week are going to be picked up by Jesus and Joshua in the coming weeks in their kind of follow-on to this course. In particular, Joshua will tell you more about some of the techniques for controlling that spectral norm error, so the error between A and its expectation in operator norm. And Jesus will tell you a bit about other methods for doing community detection in the stochastic block model, especially revolving around variational methods and the EM algorithm and things like that. So there's lots of good follow-on to what we talked about this week. But I want to talk today about kind of maybe to step back a little bit from what we've been talking about the last few days and present to you a couple of higher level open problems within network analysis and specifically within kind of spectral methods specifically. So we started this whole discussion with the stochastic block model. And under the stochastic block model, our whole task was to, well, maybe estimate B, we don't have to, but certainly recover tau, the vector of community assignments. And then we extended the stochastic block model in a few different ways, right? We incorporated notions of mixed membership. We allowed for the possibility that our vertices might differ wildly in their degrees. And then we further kind of relaxed some of those discussions to land at the random dot product graph, where our network structure is driven entirely by a kind of latent geometric structure, and the probability of an edge between any two vertices is driven by these latent positions, right? Every vertex in our network has an associated latent position in some k-dimensional space. So when we reach that level of abstraction, X, our latent positions, could represent community structure in some way or other, right? But they need not. They might be something much more general, right? In the end, we can think of X in the RDPG. Where's white chalk? I think of X in the RDPG as representing something like, let's do it this way. As representing something like the roles of each of our vertices, right? So somehow or other, xi, the ith row of capital X here, represents a role. I'm putting that in big quotes, but somehow or other represents or encodes the way that vertex I tends to behave. So we could imagine just looking at some region where all pairs of points have inner products between 0 and 1 and just throwing down some points in that region and having those points drive network structure. Those points need not have a cluster structure, right? I can draw a bunch of points in Euclidean space and they don't have to necessarily cluster. We might hope that they do, but they need not, right? The structure present in X is far more general than just a stochastic block model. I have never lectured while this sweaty. I climbed up that big hill, and now I have to be sweaty on camera about it. I hear the camera makes everyone look really dry. Yeah. The point I want to make here is that spectral methods, when we expand that notion to mean anything that might try to work with something like X or the eigenvectors of A or something like that, spectral methods are much more general than just clustering. Right? I mean, clustering and community detection are kind of the fundamental problem in our field, right? Generally speaking, when we think about networks, it's just kind of most natural to think about there being some kind of community structure. But I want to stress that it's not the only problem out there, right? And I think sometimes in our field, we get so hung up on community detection that we forget that there are other problems we might care about, right? So some of those problems you'll talk about in the coming weeks. Just mentioned these other kinds of problems, for example, graph matching. Right? So what if I have two graphs, right? for example, they might represent two different social networks. And I want to figure out, okay, if a user in this social network, what is their username in the other social network? Jesus will tell you more about this problem in the coming days, but let's just think about one way we could do this using these random dot product graph kinds of models. Right? Say I have two networks. One has latent positions x and one has latent positions y. If there's an alignment between x and y, meaning I can rotate one to look like the other, I should be able to use estimates of the latent positions to assess whether or not these two graphs are similar. Okay? So graph matching, there's a related say maybe network comparison. And so for work on that, there's lots of papers out of Carrie Preeb's group basically looking at problems where I say, here's two networks. Do they have the same latent positions, the same x's or not? Right? This kind of application shows up in neuroimaging. Right? So for example, there's a very famous data set, the COBRA data set, where we have fMRI scans from healthy patients and schizophrenic patients. And you might want to ask, does the average connectome, the average graph representing brain structure, look the same between healthy and schizophrenic patients? Right? There we might want to compare two or more networks. Okay. Near and dear to my own heart, just because it's something I'm working on a lot lately, network regression. Right? So I get a network, and I observe some response at each one of the vertices. For example, I might say, I have a social network of who interacts with whom, and I see a response of who got sick in the last week and who didn't. Right? I could be studying kind of how a disease is spreading in a community. Right? We might want to predict some node-level response from what we know about the network and about the people in that network. So I list these problems not because we're going to go into great detail about them here, but just to stress that there are other areas of statistics where we care about these kinds of models and where community structure is not so obviously central to the story. Right? So again, to stress that these methods are not just for community detection, and if we evaluate them only in terms of community detection, I think we may lose the forest for the trees. Okay. So our crown jewel result of this week was basically control of this error under the RDPG. We always minimize over Q here. And we argued yesterday for why the kind of right notion of distance here is the 2 to infinity norm. Right? It gives us uniform control in recovery of all of the latent positions, all of these x1 to xn. Right? Now, we chose x hat here. So if we remember that, we'll write that x transpose equals u s1 half u s1 half transpose. And we chose x hat to be u hat s hat 1 half. Here, u hat, let's write it here. U hat is the leading k eigenvectors of A. Right, and S hat is the same leading eigenvalues. Okay. We chose x hat in this way basically by the plug-in principle, looking at one expression for x and saying, well, okay, if I could estimate u and I could estimate s, we'd be done. So we do that. This is called the adjacency spectral embedding, right? We can think of the rows of x hat as each representing approximately these, each one kind of approximately capturing these x's, and under the interpretation where these xi's, these latent positions, describe vertex roles, we can think of this x hat as an embedding of the network, meaning a Euclidean representation of the vertices in my network that somehow preserves some notion of similarity that we might care about. The adjacency spectral embedding. And that was studied by my academic brother, Dan Sussman in his thesis work. And in particular, this paper where it was first developed is Sussman, Tang, Fishkind, and Priebe. So again, more of that Hopkins crowd. And that's 2012. Okay, so this is one way, this procedure is one way of taking a network and getting vector representations of the vertices. And if our network came from this model in actual fact, then these x hats recover these x's up to some rotation. But even if my network A didn't come from such a model, you just hand me a network, if I want to visualize this network, right, if I want to get some kind of low-dimensional representation of the vertices, well, x hat is a perfectly good choice. Even if A didn't necessarily come from such a model. It's just that then we can't argue that the x hats are estimating anything in particular. So we chose x hat here because it matched x under this particular model. But there are lots of other procedures kind of like this that take a network and produce vector representations of the vertices. I'll just briefly list a couple of them. Or maybe let's see why might you consider other things? Let's think back to our very first lecture where we said that in the SBM with B equal to something times P, Q, Q, P, all the information about cluster membership was carried in that second eigenvector. So here's a situation where if we knew for sure that our true model was a balanced stochastic block model, right? Same number of vertices in both communities. And furthermore, that B had this structure, right? P and P on the diagonal, Q and Q. So my two communities talk within themselves with the same probability, right? Very, very highly structured model. But if it were true, then all I'd have to do is look at the second eigenvector. This motivates a different kind of embedding than this, right? If I really think that this model is the truth, I should be ignoring the spectrum altogether. I should just look at the eigenstructure, right? Right? That is to say, under this very specific setting, really only cared about U, the eigenvectors, not about the scalings of them by S. Okay? Now this motivates a different choice of embedding. This motivates what I call, I guess, typically a kind of classical spectral clustering. And maybe like a sign that you're starting to get old is that like you refer to things as classical that were invented after you were born. That was an okay joke, and no one, come on. Okay, like classical, okay, this is like 20 years old, if that, right? But take the eigenvectors of A, like U hat, right? All right, I'll just write it in one sentence, right? You k-means or other clustering, whatever you like, you just k-means cluster the rows of U hat. Right? So already we see two different methods for producing embeddings, two different ways of doing spectral clustering. One is I could get my x hat here, right? I take U hat and scale it by square roots of the eigenvalues. And I cluster the rows of that, right? Cluster the x hats. Or we can argue on the board in a hand-wavy sense, and you can like show a little more formally in these very structured settings that it's actually better to just look at U. Right? I should ignore the eigenvectors, or excuse me, the eigenvalues altogether. Right? I mean, you can show that U hat minus U Q in 2 to infinity norm is small And that uses kind of similar tools to what we saw yesterday. And in particular, Joshua, who will be picking up where I'm leaving off here, has a great paper about this that will also tell you everything you ever wanted to know about the 2 to infinity norm. Cape, Tang, and Krieb. So this bounds on this guy instead of on x hat minus x can be found in this paper. That's 2018. Okay. So we've got 2 different embeddings. You give me a network, I have at least 2 options. I can look at x hat, right, the scaled eigenvectors, or I can look at just u hat, the unscaled eigenvectors. It gets worse. Why do we have to look at the adjacency matrix? Why A? Those of us who know a little bit about spectral graph theory might argue why maybe you look at the graph Laplacian. Okay, so for those not familiar, that's L. Okay, one of the several varieties, or several flavors of graph Laplacian. Right, take the adjacency matrix and rescale the edges by kind of reciprocals of square roots of the degrees. So D here is the diagonal matrix of the degrees. Oh my gosh. Okay, with the convention that if a degree is 0, the inverse square root is also 0. Okay. For a nice sort of review of this, Fan Chung's textbook goes into great detail about some of the fun combinatorial properties of some of these objects, nice connections to other branches of mathematics as well. Okay. So now we have even more problems. If you hand me a network, I have to make 2 decisions. Do I use the graph Laplacian, or do I use the adjacency matrix? And do I scale the eigenvectors or not? Okay. It gets even worse. High and low degree vertices in A cause problems for the concentration of A about its mean and for L about its mean. And so typically what we have to do is either remove very high and very low degree vertices or do something else like regularization. Right? So I'll call it maybe network pruning. Which is a term I'm literally making up on the spot, but like again, we kind of trim off the vertices that cause problems for the stability of these embeddings, right? Or regularization. Can you tell that I'm finishing a paper about network regression by how often I say regression when I mean regularization? Okay. Right? So for example, regularizing might mean that I instead of looking at A, I look at like A tilde, and the edges of A tilde are Aij plus some small amount little r. Right? And that way, all of my small degree vertices will have a degree at least n times little r. And all of my high degree vertices, well, their degree will be even higher, but it won't, the mismatch in scale will not be quite so bad. Okay, so I guess on that, I'll just mention 2 papers out of, this is not at all a comprehensive list. Conley, Lisa Levina, and Roman Vershinin have a nice paper on this. 2017, and then Carl Rowe and one of his students in 2013. Just two examples. This the subliterature on how to go about this is vast, and Jesus will tell you a little bit about that stuff in the next couple of weeks. That is correct, right? Okay, good. And now you get to hold Jesus to it. It'll tell you all about this stuff. Okay, now I have 3 or more problems. Again, these are problems for practitioners, right? As mathematicians, we get to pick whatever, pick whatever you want. But if you come to me with a network that you collected out there in the real world, and we're going to analyze it using something in this family of methods, we have to make all of these decisions. And you might hope, well, one of these procedures is going to have especially nice mathematical properties, and we'll just always use that. But it's bad news. I mean, it's interesting news, but it's bad. Right? I'm not even going to bother to write this out, so that we have good empirical evidence that no one of these different choices dominates. So we can cook up examples where spectral clustering on the Laplacian is better than on the adjacency matrix and vice versa. We can cook up examples where using the eigenvectors is better than using the scaled eigenvectors, that using u hat is better than x hat, and vice versa. So open question, and this is frustrating because we usually like to have open questions in mathematics are usually like we're going to write a very specific problem setup. This is far more general a project. Open question. Characterize which spectral methods are appropriate for which model settings. Right? So if I knew something about B in the SBM, or if I knew something about the structure of these X's, or anything like that, would that help me to decide which of these different combinations of decisions, of analysis decisions, I should take? Okay? So I mean in particular things like, if I know that I'm in a very sparse SBM, is it better to use u hat or x? Just for example. Okay, so things like sparsity, balanced versus imbalanced cluster sizes here, right? So are the cluster sizes the same or not, right? If one of the communities is much bigger than the other, that might mean that looking just at the eigenvectors is bad because your eigenvectors are going to be localized, right? Or one of your eigenvectors will be localized. Or what if B looks more like a planted partition model? What if I have P1 and P2 on the diagonal, and P1 is much bigger than P2, right? So if there's additional structure in B that takes it away from this balanced case, what should our decision be? Okay. This same group of authors, so Joshua along with Min Tong and Carrie Prieb, have a paper that takes a step in this direction that looks specifically at this kind of if P1 is bigger than P2 or not, right? If they can kind of characterize to an extent. Whoops, Joshua's last name is not Joshua, it's Cape. This is in 2019. Just as an example, right? So this paper looks specifically, say e.g., for example, this paper looks specifically at what happens when B has, one of the on-diagonal block parameters is much bigger than the other. Okay. And again, they can at least show at a kind of high level that there's a sort of transition between when the Laplacian is better and when looking at just the adjacency matrix is better. Okay. I want to spend our last 15 minutes or so talking about another kind of open question. So I'm going to write it on the same chunk of board. On the very first day, I mentioned how we were going to be assuming that k, the number of clusters, right, or the dimension of x, was known to us. But of course, when our scientific collaborators come to us with data, that's not the case, right? No one ever shows up, at your office door with a network and says like, help me analyze this network. I know for sure it has 8 clusters, right? That just doesn't happen. So as statisticians, the very first thing we have to do when fitting one of these models is pick what the heck this k should be, right? That's step 0. It's before I can even do any of this model fitting or analysis or anything like that, right? Very first thing we have to think about. And unfortunately, it's sort of the hardest step here. So, open question. How do I choose k based on A? That is to say, i.e. on my data. Right? Once again, this is this kind of like, it's a strange way to think at first if you're trained in probability theory. Right? We always think about, there's a model, and then I want to talk about properties of A. Now we got to go the other way. I see A. What family of models did A come from? What was, even if I tell you, I promise this is from an RDPG, but I won't tell you which K, what K was. Can you figure that out? This is an example of what's called model selection in statistics. So for example, we heard about the lasso the other day, right? How do we choose which variables to keep in a regression or not? Right? Similar kind of problem. How many dimensions should I keep in my model? So let's step back and look at the kind of a simpler problem. I think, oh, yeah, of course.
Question. Is there any paper related to this question?
To the second one? Yeah. Yes, there's a bunch. And I'll talk about them. Yes, the question was like, has anyone thought about this before and written about it? And of course, yes. This is like.
Can you point some reference?
Yeah, I will. Yeah. And furthermore, the lecture notes that I post will have a whole bibliography on this. So anyone who's watching this and gets upset that I forget to like list their paper, the lecture notes will have it, I promise. So let's step back and think about a simpler problem. This is more of a classical statistics hypothesis testing problem, but I want to mention it to kind of fix everyone's thinking, especially for those who maybe haven't taken a stats course in a while. So let's say I have data x1, x2, blah, 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 xn. And these x's don't have to be the same as those x's. They're an IID from some distribution f. Okay? And I know that either f equals f naught or f equals f1. Okay, so somehow or other we've narrowed things down to just two possible distributions. Right? But we just don't know which one. But we get to see a bunch of data from whichever distribution that is. Okay? So how might we determine whether f equals f naught or f equals f1? And this is kind of the fundamental problem of hypothesis testing. In statistics. Right? What we want is a procedure that takes this data and spits out a decision, right? 0 or 1. Like, here's some data, you tell me, am I f0 or f1? So we want some procedure, say delta sub n. It takes x1 to xn, right? And it spits out 0 or 1, corresponding to which of these two distributions we think the data came from. Okay, and ideally, we'd like this thing to be right most of the time. In other words, the probability, I'll write so probability under f sub k, that delta n on the data does not equal k is small. Right, if we do everything well anyway, and this is for k in 0, 1. Right? That would be the best anyway, right? Right? In other words, with high probability in the colloquial sense, right, with probability that's not negligible, hopefully we get this question correct. I'll just give an example, right? But it's a, kind of the example. So common choice is the likelihood ratio. I'm just going to write that as LR to save time writing. Likelihood ratio. Right? It's exactly what it sounds like. How do I tell which of these two distributions my data came from? Well, let's look at the probability, or really strictly speaking, the likelihood under each of these models, and just compare them. And if the likelihood under one model is much bigger than the other, well, it's probably the case that the data came from that model. Right? So we could look at something like L sub n, and I'm sorry, this capital L is unrelated to that one. This one has an n on it, so it's obviously different. x1 to xn, and this will be, we'll take a product over our data, and we'll evaluate f0, f1, and here, I'll just add up here, these have densities or PMFs. Fk, k equals 0, 1. Okay, so little f here is just the density or PMF, depending on whether our data is discrete or continuous, of the two distributions. Okay, so if this quantity here is big, that means that generally speaking, the way I explain this to my undergrads is right, when the likelihood is big, it means that the model likes the data. Everyone else should start using that too, so they don't seem like such a psychopath when I talk to my students. Okay, right, so when this ratio is big, f naught explains the x's better than f1, right? And if this ratio is really big, we're going to say, all right, the data must have come from f naught. Right? On the other hand, if this ratio is close to 0, right, much smaller than 1, then we're going to say, well, clearly, the data was not very well explained by the f naughts, but it was very well explained by the f1s. Okay? In other words, when this is big, that's evidence in favor of f naught being the truth. When this is small, then evidence in favor of f1 being the truth. And the challenge is to pick what we mean by big or small. Right? What we'll do in the end is choose some threshold. I'm not going to go into this in great detail. If you want to see the careful treatment of all of this, any introductory stats textbook will have it. You're looking for the Neiman-Pearson hypothesis testing framework. I'll write that on the board in the lecture notes. But, the idea, right, delta n of x1 to xn is the indicator of whether ln is, bigger than or, we choose f1 when this thing is smaller than some threshold little c. Maybe we should call it little c. No, just call it c. It's going to depend on some other stuff, but we're going to glaze past that other stuff because of time. Okay. So if we choose this threshold c correctly, we can basically minimize this probability of error. Okay? And so those of you who have seen the Neiman-Pearson hypothesis testing framework before, right, I'm trading type 1 error against type 2 error. That's this exact same story. Okay? So this is how this story all works out in kind of classical statistics. Our problem now is a little more complicated because I'm not testing one specific distribution against another specific distribution. I'm testing whole families of distributions against each other. I'm asking, in the simplest case, suppose I give you a network and I say, I promise this thing is either a 1-block SBM, namely an Erdos-Renyi random graph, or a 2-block SBM. Right? Tell me which one. Right? The problem here is that in this kind of classical setting, I'm comparing just, one distribution against another. Right? More generally here, I'm comparing whole families of distributions. Okay? So, and it gets worse. Like if you were just comparing two families of distributions, you would just be in, a composite setting of this kind of hypothesis testing framework. Right? I'm asking like, okay, F is some member of one family of distributions, or F is from another. Things get much more complicated here. So maybe just one maybe more concrete version of this open question, right? Suppose I tell you, here's a network, and it came from the random dot product graph. Can you find for me a statistic, which means a function that takes in data and spits out a number or a vector or something? Find for me some function of the data that behaves in one way if the data came from a k-dimensional RDPG or a k-block model, and behaves in a very different way if it came from a model with k-prime blocks. Right? To borrow the phrasing from Mickey's lecture, was that yesterday or 2 days ago, I want a statistic that is distinguishing. Its behavior under different distributions, under different models here, should be very different. Right? Okay. Now, as I mentioned, people have thought about this. I'm going to I'm not even going to write all the citations here. I will say them, and they will be in the lecture notes that I post. So to my knowledge, the first method to try and get at this was due to Zhu and Godse in 2006. They did what I think many of us still do, at least during the exploratory phase of network analysis, which is just look at the scree plot. Like plot the eigenvalues from largest magnitude to smallest magnitude, and just look. And oftentimes, in simpler versions of these models, there's an obvious jump. Right? There will be some point at which you're like, OK, eigenvalues are big, 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 and suddenly there's a giant gap, and they're small. Okay. Sadly for us, as soon as there's any kind of interesting structure or interesting noise in the network, it gets a lot hazier. So it's very hard to do this test by eye. Okay? But Zhu and Godse were the first to kind of at least give a heuristic argument for why you should look for a particular change in the scree plot, namely in the sequence of eigenvalues. Okay. So this works actually very well in practice. It's kind of the standard thing that most of us in Kerry Preeb's group writ large, like those of us who graduated out of his group, I think most of us still use it as a kind of baseline method to compare against. But it's entirely based on a heuristic. We don't have good theory for why this thing should work. There's a couple of recent results that use random matrix theory. The basic intuition is that if, for example, my data came from an Erdős-Rényi random graph, Erdős-Rényi NP. Right? Okay, for those of you who really like the G, I'll write G here too, whichever one you prefer. Right? If I construct a different matrix, A tilde equal to A minus, or maybe I'll define this edgewise. Right? A tilde constructed in this way is a Wigner matrix. Or I guess if we're being very strict here, this is a generalized Wigner matrix. Up to a little bit of stuff on the diagonal that can be taken care of that's done in the paper. So there are two papers that kind of follow this basic idea. One is due to Jinglei in 2016. Yep. And then also work by Peter Bickel and Purna Sarkar. Okay. The important idea here is that I would have to estimate, if I plug in p hat, basically plugging p hat in for p doesn't break the Wignerness, doesn't ruin the spectral behavior. Okay, the reason we care about this, excuse me. Oh, yeah, that's right. So A tilde being a Wigner matrix, in particular, we can use the fact that then the largest eigenvalue, suitably recentered and rescaled, has very well-known behavior, according to the Tracy-Woodham-1 law. So we know what the distribution of that largest eigenvalue should be if this were true, right? So if this were true, you look at this guy, you put hats on the p's, and we know basically the behavior of this thing. And then you would look and say, well, if that largest eigenvalue, suitably rescaled, recentered, everything, doesn't look like it could have come from the Tracy-Woodham-1 law, that's evidence against this model, namely against having only one block. Okay? And then you have to kind of complicatedly recurse, because now you say, OK, well, I'm not a one-block model. I'm a two or more block model. What do I do? Okay, so details on that, of course, are in these two papers. Okay. I'd be remiss if I don't mention that Andressa has a series of papers on this. I'm just going to write, Andressa, I'm sorry, you have like 4 papers on this. So et al. And what, there's like 2016-ish to recently, right? Like to like now. Andressa has a series of papers that used variations on likelihood or penalized likelihood methods. So basically, if you kind of squint hard enough, it's in this same family, right? You say, suppose I came from such and such a model, what would the likelihood look like? And if that likelihood is especially small, that's evidence against that model, right? That's the best like 2-sentence summary of, like, it's a whole series of papers which I highly recommend you read because they're really fun. Aha! All right, so next Thursday, Andressa is going to blow up this little corner of the board into the whole board, or into the slides for you. Okay, so look forward to that. I'm really sad I won't be here for that, because I really like these papers. I'm going to embarrass you briefly. I remember when Andressa was writing, I guess it was the second in this series of papers, with our shared postdoc supervisor, Levin. So I remember when like the first of these papers was being written, and now there's like a whole garden has bloomed from them. It's really lovely. So if you want to hear more about these, just ask Andressa, not me, because it'd be silly to ask me. OK, we have 5 minutes, and I want to mention one last series of papers on these, and they are, I want to mention them mostly because they use like a neat probabilistic trick, but I'm not going to be able to do it justice in 3 minutes. I'm going to give a very hand-wavy sketch. These are a family of methods based on cross-validation. So in statistics, cross-validation is basically, if you're familiar with machine learning, right, we have the train test split, right? I take my data and I set some of it aside. I train my model, I fit my model to some of the data. And then to assess how good my model is, well, I can't assess my model on the data that I fit to. That's cheating, right? That's like, you know, you give undergrads a practice exam and then their real exam is the same exam. I mean, the undergrads love that, but like, it's cheating, right? If we're doing machine learning, it's cheating. Okay, so the basic idea is that I'm going to set aside some of my data and kind of evaluate, you know, fit a model from one part of the data, and then I'm going to evaluate it on the rest. Okay, now, classically, cross-validation involves independent data, right? Someone comes to you and says, like, here's a bunch of experiments I ran. They're all kind of, we can model them as being independent of one another. And so it's safe to just like take a few of them at random and set them aside to use later. Right? In a network, it's not nearly so obvious how to do that, right? Because like networks are very dependent, right? But under things like the random dot product graph and under the SBM, if we imagine that the cluster memberships are drawn IID, there's a latent variable that is independent. Okay? And so you can often take advantage of the conditional independence of the edges to get something like cross-validation nonetheless. Okay, so I'll just mention a few of those papers here. There's work by Zhenxi Li, Lisa Levin, and Ji Xu. That's in 2018, 2020. So CV methods. Work by Chen and Lei. 2018, and then work out of Yinging Fan's group more recently. We have 1 minute. I want to sketch one other trick for this, because I just think it's cool, and it's a nice example of how like probability theory genuinely can like help what we do. And the next time you hear a statistician say something mean about the probabilists, remind them about this result. Okay, Chen, Roche, Rowe. So Sebastian Roche and Carl Rowe are my colleagues at Wisconsin. The paper that's posted on the archive during the pandemic. Here's the idea. The expected value of A has eigenvalues. Lambda 1 down to lambda k. Oops. And 0 equals lambda k plus 1, and so on. Okay, so my first k eigenvalues are non-zero. All the rest are 0, right? That's true in all these models as long as things are kind of full rank. And I have eigenvectors u1, u2, blah, 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 down to un. Okay? Let's recall from our sketches yesterday, if I look at these quadratic forms, this thing is going to concentrate about 0. right? And in fact, if I rescale it, if I divide through by the right variance here, I'll get that this thing goes to a normal asymptotically, right? So if we knew u1 down to un, the true eigenvectors of the expected value of A, we'd be home free. We could look at these inner products for u1, u2 up to uk, and so on, right? And use these to estimate which of the eigenvalues are far from 0, because uk transpose A uk would be like the true lambda little k plus some small stuff. OP, let's say. Right? Okay, but we don't know these guys. If we had two independent networks, we'd be golden, right? I could estimate these eigenvectors from one of them. I could use u hat from one, and then I could evaluate these quadratic forms on the other. But we only ever get to see one network, unless we're in like multiple network land, which Jesus will tell you about a little bit in the coming weeks. Chen and co-authors use something very clever. They use the fact that Poisson random variables have the splitting property, this thinning property, where I can multiply a Poisson, right, by a binomial, right? And suddenly I have two independent Poissons. So do that to every edge of A, if A is Poisson, right? If the edges of A are Poisson. You can take A and generate two independent copies. They have the same expected eigenstructure, just scaled by the parameters of the multinomial. So again, a neat trick from probability theory gives you a nice way to solve this problem in a kind of like principled manner when A comes from a Poisson, right? Now, if the entries of P are very small, like if I'm in a Bernoulli network, but the entries of P are small, then there's a good approximation theorem that sort of lets you push all this through. Okay? So just a nice, clever use of probability theory to do something like practical and rather urgent for network science. Okay, I've already run 3 minutes over. I want to take literally a minute to thank again, first of all, the organizers and the team here for all of their hard work keeping things running, and for the invitation to come and speak with all of you. I want to thank you all for showing up all 4 days and asking great questions and paying attention. I promise to post lecture notes that will fill in lots of details here as soon as I'm at my computer for more than like 30 minutes and not on a plane. So thank you all once again, and I'm happy to stick around for a little while and chat. Thanks so much.